So today I'm gonna give an overview of dwarf galaxy science and try to answer the question why we are interested in studying the faintest galaxies in the universe, and some may also say the most unimpressive galaxies. So first of all, it's a multidisciplinary audience, so I will at least try to get you on the map what's galaxy. So most of the matter that we can directly detect in the universe are in the forms of gas, stars, and dust. This is the matter mostly consisting the universe. But this matter is not randomly distributed in space. It's actually distributed in the gravitationally bound units, which we call galaxies. And they look more or less like this, and our Milky Way is one example of this kind of entity, galaxy. Of course, universe is hierarchical, so galaxies also form larger structures. They are part of galaxy groups and clusters, and which are not randomly distributed in the space, but they are distributed in this large-scale structure that we call cosmic web. So one can state, and it's often stated, that the galaxies are building blocks of the universe. So the large-scale structure are consisting of the galaxies, but of course galaxies consist of smaller scale things. Okay, and how do galaxies look like? I guess most people, when they hear the word galaxy, think about objects like this. And it's true, those are galaxies. Those are actually very big galaxies, and our Milky Way could be similar to object at the top of the right side of the panel. But not all galaxies are big and beautiful. There's also galaxies like this on the left. So these are the dwarf galaxies. So if we look at the total luminosity of the galaxies versus the surface brightness of the galaxies, both increasing to the right and up, the big galaxies are bright, and then there's small galaxies that are very faint, and they are very difficult to find and see from the night sky. Okay, so one could easily say that, okay, those are tiny, those are maybe consisting of thousands or tens of thousands of stars, and these might have tens of billions of stars. So why care about this? Okay, if we look at the numbers of galaxies, so from large mass to small mass, the number distribution of the galaxies goes like this. So actually, if we think about those large, beautiful galaxies, they are very few, and most of the galaxies in the universe are actually like these small guys on the left. So it's obvious that if we want to understand the universe, we need to understand the majority of the galaxies. Okay, and to make it even more understandable why we want to study these galaxies, actually many of the current tensions with the observable universe and our best cosmological models are related to dwarf galaxies. Don't try to understand this yet. We will come back to this slide after I first explain what is our cosmological model and how we came up with that. Okay. First, about galaxies. We understood that galaxies are separate entities from our Milky Way about 100 years ago, and we started studying the mass budget and properties of galaxies soon after. This is an image from 1939 that shows the Andromeda galaxy with actually quite poor picture, and this is the rotation curve of that galaxy. And why do astronomers want to study the rotation curve of galaxy? So it's basically the velocity of stars at given distance from the center of the galaxy. That's because one can actually measure the mass inside given radius by measuring the velocities of star at given radius. And already that time, the astronomers realized, okay, it seems that the most of the mass that we can observe are in the very central parts of the galaxies. But still, the rotation curves of the galaxies, they keep rising and stay constant at the very far distances from the center, where we actually don't see any matter. And that hinted us that there should be either modification of our gravitational laws and dynamics, or there's a hidden mass component that simply cannot be observed, so it's not emitting light. Similar conclusions also came from the analysis of galaxy clusters based on gravitational lensing that can be used to trace the total mass of a given structure, and also from the galaxy cluster dynamics. Similar manner we can compare the kinematics of a cluster with its measurable or the observable mass, and we always find this discrepancy that most of the mass is actually missing in all these different scales. And that slowly led to the conclusion that there must be a missing mass component in the universe that is not interacting with electromagnetic waves, so we cannot see it. And that's actually the postulation of the dark matter. So that's one part of our cosmological model. Then in mid 20th century, there was also observation that if we look at the galaxies, the further they are, the more quickly they are receding from us. So it seems that all the galaxies are going away from us, and actually when we look at the galaxies that are further from us, they are receding with the faster velocities. And if we don't want to make the old mistakes of thinking that we are in the center of the universe, we need to conclude that the space should be appearing similar in different locations. So only explanation that can produce this observable thing, and with combined the idea that we are not in the center of the universe is the expanding space. And then when one rewinds the tape to the beginning, there must be a point in the time when the universe was very small, because it has been expanding. So that's the idea of the dark energy, so the component that expands the universe and space. So okay, in early 2000s, the computers started to be powerful enough to make very large particle simulations. And people started to then simulate the universe, starting from these very basic ideas that there's matter in the universe and the universe expanding. Based on the galaxy analysis, it was evident that most of the matter is dark. So actually we can take a zeroth order estimation that all the matter is dark. So people started with these kind of dark matter only simulations, like the Millennium Run here. And they simulated a box which was filled with the dark matter, matched with our cosmological observables, and then let that box with the given initial conditions to expand and the dark matter to gravitationally interact with itself. And what comes out is surprisingly looks like this. This is more or less similar structures that we see in the observable universe. So there seems to be some kind of web structure forming in these dark matter only simulations. And when one zooms in, one can see that there's actually these kind of dark matter halos that could be interpreted as the dark parts of our galaxies. So okay, people were very happy. There seems to be nice match with our large-scale structure of the universe, and there seems to be galaxies forming with these very simple assumptions. But when these first results were compared with the actual observations, problems start to arise. So this is the mass function of the galaxies obtained from the observations of real universe, and the dashed line here is the mass function of the dark matter halos. So it seems that the mass function of the dark matter halos, so the mass function is number of halos at given mass, seems to be having a different shape than the actual observable galaxy mass function. Okay, that's evidently a problem, but there was quickly a solution for that. So it's a very good assumption that the dark mass of the galaxies correlates with the amount of luminous mass or baryonic mass in the galaxies. So the solution was to put these most massive observable galaxies into these most massive dark halos, and this is one by one, you match the halos with the luminous parts of the galaxies. And as the shapes of these mass functions are different, one gets this kind of stellar to halo mass function. So it tells basically that how much dark matter, or in this case actually luminous matter there are in the galaxies as compared to the dark part. So it basically shows that in the most massive galaxies they are dominated very strongly by dark matter. Then in about Milky Way sized galaxies they have much more baryonic matter with respect to the dark matter, and the lowest mass galaxies again are the most dark matter dominated galaxies. Okay, and actually this is theoretical prediction, and people actually then started tracking the dark matter content in the different mass galaxies. And nowadays it's confirmed, both in the high mass end and low mass end, that when one goes to the lower masses, the dynamical mass compared to the stellar mass of the galaxies goes up. So it's the same thing as saying that galaxies become more and more dark matter dominated. So it's very nice. The observable universe seems to be behaving similarly as this abundance matching solution to this mismatch of dark matter only simulations and the real universe. But then there's a question. Why do these small galaxies are dark matter dominated? Why they fail to form normal matter in the same amount or same fraction as the more massive galaxies? What causes them to have very little baryonic matter in them? And that's actually a very difficult question. One cannot solve that by using only the dark matter only simulations, but there was a requirement to simulate also the baryonic component of the universe, and that's extremely difficult task. So now you need to add the gas, the dust, the stars, simulate how stars form from the gas and how they interact with the gas, how magnetic fields interact with the gas, all that kind of stuff. It's terribly difficult work. But in last decade, people have been doing this, and actually from these very complicated simulations, what comes out are these kind of galaxies shown here in these 5 panels. This is actual galaxy observed with the Hubble Space Telescope. So it seems that we are getting right kind of things out of those galaxies. So at least they are doing something right in those simulations. And okay, we also get the stellar to halo mass relation more or less right, and we get realistic galaxies. But the problems arise when we start to look at the details. So now back to this slide. So this is a work by Laura Sales et al. From 2 years ago, and she is listing all the problems that are concerning dwarf galaxies and their current cosmological models. They are with the group with different levels of tension or severity of the problems. There's, it's not clear whether the stellar to halo mass relation is completely right. There's uncertainties in the computer models and also in the observations. There's problem that dark matter halos seem to be typically in the simulations form very dense cores, but dwarf galaxies don't seem to form that kind of things. So there seems to be a problem. But on the other hand, the mass profiles of the actual real dwarf galaxies are very hard to measure, so there's observational uncertainty. Then there's a bit more severe problems. When looking at the galaxy groups in real universe and simulations, in real universe they seem to be missing the most massive dwarf galaxies. There's just the biggest dwarf galaxies one can find as which are satellites of bigger galaxies are always too small in the real universe. There's also there a bit of observational uncertainty. I'm not sure if the samples are complete enough. Then in real universe, the dwarfs have a very wide range of different sizes. At given mass, they can be on the order of tens of light years or hundreds or tens of thousands of light years. And it's very difficult to form that kind of diversity in the simulations, and actually that's not happening in any of the current simulations, so it's unclear whether this can be solved. Also, other part of that problem is that we actually are not sure even if we can observe the most diffuse and most compact dwarf galaxies. Then, in order to make the dark matter to normal matter ratios in the low mass galaxies very high. People have put very strong feedback mechanisms in this simulation. And by feedback mechanism, I'm meaning of models that prevent star formation, that heat gas or expel gas from the galaxies. So things like supernova that blow up the whole gas component out of the galaxy, and no stars form anymore. And that's very effective in making the low mass galaxies poor in forming stars, but in real universe we see very low mass galaxies that are forming stars. So there's now difficulty in at the same time matching the stellar to halo mass relation and also leaving some galaxies there that still form stars. So it's not clear whether this can be solved in these simulations. Then there's even more severe problems, which might not be even related to the simulation recipes or anything like that. They might be related to the fact that, or at least one possibility that the whole cosmological model is wrong. One very interesting thing is the satellite planes. If we look at the dwarf galaxies around the Milky Way, they are not randomly distributed, but they are actually mostly condensated in a thin plane that's rotated around Milky Way. And also in Andromeda, and also in some other the best studied galaxy groups in nearby universe. And that's a thing that doesn't appear in the cosmological simulations. And that cannot have anything to do with the baryonic properties, because the numbers and the distribution is related of galaxies in the cold dark matter universe. It's related to the properties of dark matter halos, and that you cannot just simply form from in current cosmological model these kind of satellite planes in significant amount of galaxy groups. But there's also a thing that it's not clear whether how significant this thing is statistically. We just have a couple of nearby groups that we have observed. So I'm pointing here to these problems and tensors that are at least partly unclear still on the observational side. I'm an observational astronomer, even though I've been speaking mostly about simulations so far, but I want to motivate why it's so important to make accurate observations of dwarf galaxies. So this might have at least partly, or this could be partly solved by observations, partly by improving or changing things in our simulations, or if we first study the whole range of possible theoretical models in the simulations and make sure that our observations are very good, then the last thing is, if these problems still exist, is to change our cosmological model. But first we need to be sure that the observations and the simulations are as good as they should be. So, as an observational astronomer studying the dwarf galaxies, my aim is to make as complete as possible view of the dwarf galaxies in the local nearby universe. In principle, this has three parts. First, we need to get very nice images, produce very sensitive data that can detect these galaxies. Then we need to find an algorithm that can reliably go through these large data sets and identify all of the objects in those images. And third, we need to figure out what fraction or which objects exactly are dwarf galaxies, because there's a lot of things in the sky that are not dwarf galaxies. I've been working for the, let's say, last 5-6 years with these three parts of this problem, and I've been producing several galaxy catalogs, but I want to make a short summary of different steps before I end my presentations. So about the datasets. So during the last decade, there has been quite significant progress in the ground-based observations, which are still the majority of astronomical observations. I'm here showing one of the instruments. I've been using the VST instrument at the ESO Chile, which we use to generate this very deep survey of one of the most nearby galaxy clusters, Fornax, and we analyzed the dwarf galaxy population there. It's very representative of the things what people have been doing for the last 10 or 20 years. So there has been several wide field of view cameras that have very large CCD detectors and very large mirrors that effectively map large areas of the sky. This is typically important because if we look at the nearby structures of the sky, they are typically large. For example, this, if one would compare this area of the sky with the half moon or with the full moon would be probably size of this panel here. So it's actually quite large area of the sky with very deep observation. It took 5 years to observe that. But the problem with the ground-based observations is always that there's the atmosphere. It causes several problems. One is that it glows, it causes noise to the data, and one thing is that it blurs all the signal that comes through it. So one thing is that compared to observations in the space, to obtain similar depth in the images, we need to integrate much longer time because of this noise coming from the atmosphere. And we can never reach similar resolution in the images as from the sky because the atmosphere blurs everything. So okay, now we have done almost everything we can do from the ground with reasonable effort, and next step is to go to space. And last summer there was a new European Space Agency project called Euclid that was launched, and it's actually a similar telescope lifted from ground to space. That's different from, for example, Hubble Space Telescope, which tries to image very small areas very accurately. But Euclid has a wide field of view, so it tries to map the whole sky. Not actually the whole sky, but 1/3 of the sky, with the observations that are deeper than from the ground and have better resolution, even 10 times better than from the ground. So we will now, in upcoming years, have the best data sets to do actual dwarf galaxy science we want to do in order to compare our observations with the simulated universes. Then there's the algorithmic side. It's been a long-standing problem in astronomy. How to identify from the noisy data very low surface brightness things. It's actually a very tricky problem. For example, in this image, you see, or maybe you don't see, but might see that there's a very faint structure that goes across this image. And these kind of things we want to automatically detect from the images. It's a quite easy task for human eye. If you look and know what you're looking for, you will probably see it. But it's actually very difficult for automated programs to detect these. And for a very long time it was actually that astronomers visually looked at the images and pointed at where the galaxies are, and it's still happening. But in a couple of last years there have been very nice steps forwards in this area, surprisingly not using machine learning but using more traditional numerical algorithms called max-tree algorithms. And these algorithms have already started to reach levels similar to human eye. This is a kind of a segmentation map that basically masks all the pixels in the image where it knows that there's objects and separates the objects from the image, and these start to be very good. And we actually demonstrated a couple of years ago using the same data set in this Fornax cluster, which we previously analyzed in different old methods, that we were able to increase the number of known dwarfs from the same data set with about 60% using new algorithms. So there's really big advantages in this area. Okay, the third part of the problem is the hardest. Actually, all these parts are very hard, but they seem to be easy once they are solved. This third part is not solved yet. So it's how to identify from the detected objects which objects out of those actually hundreds of thousands, millions, or even tens of billions of objects are the things that are interesting to me. That's a hard thing. People are investigating this problem a lot. There's all kinds of different approaches to this. One is, of course, you automatically measure some basic parameters of all the detected objects and try to use those for classifying the objects. One is looking at the morphological parameters of the objects that can be also measured from the images. One is basically taking the images and training a machine learning network to classify those. But the problem is that galaxies appear in so many different forms and so many different orientations and shapes that it's even for human classifier very difficult task to classify them in the different categories. So first you need to understand yourself more or less what should be the categories, and then you can use machine learning. Okay. We are currently working with these problems in the context of Euclid, for example, where I'm also part of the Dwarf galaxy science group. And we are also still analyzing and trying to solve these problems in the crowd-based observations. But okay, I wanted to give you a short overview of the field and why I'm interested in these dwarf galaxies. So I will not go to details with any recent studies, but I leave you with these conclusions for the talk. Thanks.